Hey, welcome back to lecture 14, and we are now moving on swiftly into part 3. So you realize that we spent a whole lot of time on part 2 for 2.5 weeks because that is the bulk of 3A. So half of the course really is understanding how to analyze forces, and believe it or not, right, that as I motivated in lecture 1, that is in some sense the essence of physics. Every physics question starts off with forces. If you can analyze the forces on an object, you can answer 80% of everything that happens in the natural world. The other bits and pieces are things. It's the rest of the rest of 3B and 3C is really just looking at new types of forces we haven't discovered yet. We haven't discussed yet that we've discovered, but we haven't discussed yet in 3A, and then look at how that affects motion. So really, as you can see, part 2 forms the core of it, studying the motion and understanding why and how things move, right? And now we move on to part 3. What is this? Well, it's about work and energy, but how does this fit in the big picture? Let's see where this goes in our story, right? We started off with part 1 about vectors, right? And then part 2 about forces. And part 3 is energy, right? Just to summarize things in one word. And then we'll go and look at part 4, which is momentum. And finally, part 5, in some sense, is angular momentum. Okay, so you see this whole course of 3A is looking at really the key words, right? These are sort of, we need to summarize the whole course in the 5 key takeaways in the whole course. These are the 5 things you should understand out of it, right? And forces is really undoubtedly the big one, right? And then if you just look at the words, the key words of each segment, these are words are very fundamental words, and you really want to know what they mean, right? In order to study physics, it's really the essence of it. Now, we have a goal of each one. For example, vectors is really the mathematics of arrows. And the key property is an arrow has a direction and a magnitude. And we realize a lot of things are better described by arrows than just numbers. It's a more powerful thing. And we've learned how to add, subtract, scale. But we haven't yet talked about scale is multiplying a scalar and a vector, right? You scale it. But how about multiplying vector and vector? We will address a little bit of it in talking about work, which is necessary. But then we look at forces, which is what I call the theory of motion, and looking at the origin of motion, why it happens, and the answer we give is forces make it happen, make motion change, not necessarily happen, but make it change, and how it changes is kinematics, right? Energy, I'll come back, but momentum is really, if you notice, so far, everything in this part is about one object. We haven't talked about 2 objects yet, and momentum is crucial when you want to study the theory of collisions. Now, collision seems awfully specific and limited, but if I change that word to interaction, it's actually more general, right? Of interactions, collisions and interactions. So that's where we start to, you'll see, that's one of the reasons why I claim physics is a simple subject, because you spend over half of the course looking at just one object before you even look at interactions, right? And then, even when we get there, we're only looking at interactions of 2 objects. So it's going to be very simple. Everything, most of the time, try not to overthink things. We're reducing to the most ideal cases. And if you can understand that, then we should start add on the complications. Don't add yourself. Don't make your life more complicated than it needs to be when you first start, right? So that's the goal. And then lastly is the theory of rotations. Okay. We talked a little bit about circular motion, but that's not really rotation. Rotation is an object spinning around itself. In some sense, that is the first part where we are going to extend our analysis to assuming objects are not 0-dimension point particles. Remember when I say draw a free body diagram, assume things are a point, everything First of all, even though if your object is extended, it's an extended object, you want to treat it, or you can almost treat it as a point mass. At the point, so because even if it's extended, all the forces I told you to analyze, right, starts from the center of mass of the object, which means you could basically you ignore the fact that it has a size, and you just analyze everything as if the forces originate on its center of mass. All the analysis is the same. So really from part 1 to part 4, every object is really, you can treat it as a point. And part 5 is finally we address the fact that things could have an extent. It has a size. And now what's the first thing it will affect? The fact that it has a size is we can look at rotation. All right. So that's sort of the plan for the next week or so. So what does energy, how does that fit in? Well, that is really nothing new. It's really same thing, studying the theory of motion, but it's an alternative theory of motion. Okay, what does that mean? That means we have the exact same goal. In fact, all of physics, if you want to study motion, there are 2 ways of doing, and now it's known as the force approach and the energy approach. So physics of motion, in fact, studying all of physics, let's make that even more general. Almost everything I know has 2 ways of doing it. The study, let's say studying physics. Right? There is the force approach and energy approach. Okay. Now, what that means is we're trying to answer the question of why and how things move. Okay, and so far our answer of why is force, right? So force, or essentially, that's the subject of dynamics, right? It's almost synonymous with saying force. How force affect motion, and how is kinematics, where force creates an acceleration that we learn, and now in kinematics you understand that acceleration, you can find the velocity, you can find the position, you can find change in position, right? Delta x, that's a change in position, which we call s, and all the kinematics variables you can study with it. So this is sort of the picture we have about the world, how it works. Now, this is one way of looking at it, and this is essentially the force approach, pioneered by Newton. And just across the pond in France, a bunch of other French scientists, pioneered by Lagrange and Laplace, a bunch of French guys, have came up with a different idea, so sort of independent on Newton, right? So just to stick it to the British. And they have their own idea. They came up with another view to answer this question of why and how things move. And they say, forget about forces. Even though we spend a big part of it, they have another way, and they look at something called energy, and we'll try to understand that. And you can basically, for most, the 80% of the next 2 topics, you can forget about everything about forces and just look at energy. All right, so it's completely a different way to analyze things. Now, why do we need to teach you 2 ways to do the same thing? Obviously, there's pros and cons for each way. And on a practical sense, to analyze certain types of motion, one way is easier than the other. Okay, and they both have pros and cons. But before we get to a practical side, let's just look at what are the pros and cons philosophically first. Force is more visual. Okay, so it's a push and a pull. An 8-year-old can understand what that is, right? If you get into a fight, you know what's a push and a pull. So it's more visual. You can draw free body diagrams. You can visualize it easier. However, the con is you're dealing with vectors, right? And I know that vectors is everyone's favorite topic. Since you first learned it, you know that I love this and I want to do this for the rest of my life. However, you've got to admit, joking aside, it is slightly, just a little bit annoying to use, right? Especially in 2D. When you have 2D, something that doesn't fall on an axis, you need to you need to resolve it. It's something, if it goes around, you need to, if something goes along a plane like this, you have to resolve into the fx, fy, I should call that x and that y. You need to do trigonometry. One of them is cosine, one of them is sine, depends on which angle you're given. So a couple of things, right? You have, even when my object is going in purely one dimension, right? You know that a block sliding down the slope is purely in the, if I define my x-axis down the slope like that, it's purely in one-dimensional motion. You still need to resolve it into two. So you need two equations to analyze 1D motion. It's not the most efficient thing in the world. And also you have trigonometry and sine and cosine starts to come in, right? The directionality matters like that. So that's the downside with dealing with vectors. On the other hand, for energy approach, that's a pro, because you only deal with scalars. So that means we're going to say something has a certain amount of energy, but energy will not have a direction. Okay, energy is just a number. Something has 5 units amount of energy. The units is going to be joules. Named after the scientist, right? But yeah, so it was 5 units, 5 joules, 13, 3, minus 5. So if the energy decrease, you will be negative. So if you can have negative numbers, you can have negative 7, 14, whatever. You can have negative numbers, but don't confuse negative with direction. When we say direction, we literally mean a spatial direction, right? Negative 15 doesn't point anywhere. Negative 17 doesn't point anywhere. It doesn't point north. It's not that, right? It's direction in the sense of its direction between its values increase or decrease, but it's just a value. It's different from a vector, which literally points. If I apply a force and it's pointing that way, right? We need to describe direction properly, but it literally points somewhere. It's put towards a certain direction. Negative 15 does not, right? We will have negative numbers, but ultimately it's a scalar. Okay, so there's no resolving. So I know you love resolving vectors, but we're not going to have that anymore in this whole, at least in the whole part of part 3. Okay, so for those who don't like vectors, you might go, well, why are you hiding this from us? Why didn't we start off doing it this way? That comes with its con. It is fundamentally more abstract. Okay, in fact, just defining energy is tricky to do. I usually start a class to encourage students to really ask questions, right? There's no stupid questions kind of approach. I give this example. I say, one student used to come up after a couple of lessons and say, hey, I know how to do all the problems, but I still don't understand what is energy. So what is energy? So it's not a dumb question at all, right? He thinks that it's a dumb question, but this is one of the deepest questions. It's very tricky to define. We'll have a definition, and I'll talk about the trickiness in the next video. But yeah, it is abstract. So these are philosophically the pros and cons for each one. On a practical side, it's just in some scenarios it's easier to do this, and in some scenario it's easier to do this. I know this usually raises immediately a lot of questions from the students. Is when you're given choices, students will be overwhelmed with choices and say, okay, when do I use which then? I'll tell you right away, right now, right off in the first video now, is if you look at a kinematics situation, first try energy approach once you've learned the method in the next couple of videos. Try that first because it's always easier if it works. If it doesn't, then use the force approach. What I mean by doesn't is not necessarily it can never work with the energy approach. It can solve every kinematics question you can think of with the energy approach. It's just we haven't taught you the more advanced skills. Okay, so there are some. So we're going to just teach you the skills that will make this approach simple, right? So put it this way: the simplest force approach compared to the simplest energy approach, the energy approach is always simpler. Okay, so try that first, and if you have it, if with the simple methods we teach you in this course does not work, then use the force approach. Okay. All right. So one more piece of advice before we start into the meat of this is about the order of things, right? We're going to talk about the definition and then about how to solve problems with it. So this is referring to either chapter 9 and 10 in my syllabus or chapter 7 and 8, I think, from the textbook. Okay, from the textbook and my syllabus, right? And one of them is work, and one of them is energy. Now, in my opinion, work is really an obsolete concept that should not be introduced anymore. It's sort of the source of a lot of students' confusion. It's better just to get rid of work and talk about energy itself. Why is that? It's the reason why we still introduce it is because the formal definition of energy requires on work. But to understand work, you kind of need to have a good concept of energy. So these things are kind of linked. So I'm going to try to present it in a different way. I think I have a good idea how to make it slightly simpler. So I'm going to present it in sort of not as clear cut because they're both will help each other in some sense. So my advice is finish all the videos about work and energy before you start reading the textbook. Okay, like I said in the first lecture, the idea of these videos and the idea of these lectures in general is to make your life easier when you read the textbook. All right, so ultimately the learning is up to yourself to learn all the things you need to learn in the syllabus. But I know reading the textbook is not the most enjoyable and exciting thing in the world. So hopefully this sort of gives you like the movie version of a novel. So you watch the movie and read the book. It will make it easier to learn from it that way. All right, so that's just a quick advice on that. And so the next couple of things we're gonna do is we're gonna look at the definition first.